Hello everyone. Today I want to talk about finite element errors, especially in fastening and joining methods. So basically, we can divide the errors in three categories. The first one is the simplification problem, which is very common because we are trying to simplify the problem as much as possible to save time. Remember that time is actually the cost of simulation. So when we say simulation is expensive, it means that it's time consuming. Now, for the simplification, what can happen is, for example, is the wrong geometry. Like your your model is not symmetrical, but you assume a symmetric model. Like you're trying to model a wheel and you consider a quarter of it or half of it. But the loading, the formations, and other, or maybe material distribution is different. So that will make your simulation wrong or with errors. Second one is wrong material. You need to consider a kind of material study to check if the material is linear or nonlinear. And then we choose the analysis type based on that. Then we have wrong loading. For example, you have a distributed load, but you sum it up and consider it as a point load, which might add some errors. You may have wrong boundary conditions, like you fix some points which in reality might be flexible enough to act as a joint. Then it's wrong analysis type of analysis. For example, you have large deformations or nonlinear material, but you still go with a static and linear analysis, so you won't get the accurate result. Then we have the numerical errors. I will explain this characterization later, which is part of the finite element code, even though you have control over options and you can change different parameters to control it, but it's not part of the model, which is integration errors and rounding errors, which are the part of mathematical and numerical solution of your model or of your finite element model. But what I want to focus on today is discretization, because this part is affecting connections, fastenings, and wherever we bond different parts. So that's why my focus is more on this part. The first type of error you may get is for choosing the wrong type or order of the element. And the third one is mesh refinement. Now I'm going to continue with some examples and I will explain each one separately. First, let's see the element types and orders, especially in NX. I skipped 1D elements. I will explain them later. But we are going to deal with 2D and 3D elements mostly. In 2D elements, the first element is triangle or tri3. This element is really bad unless for some specific uses because it's too rigid. Can't really transfer the formation because it cannot transfer a strain really good because it's too rigid. But still, it's not bad, for example, for transferring load or just joining two parts where you want to transfer the load like a rigid element. So that's where you may want to use it. Also, it's really cheap, which means it's not time consuming for the meshing. But the problem is that when you use Try 3, you really need to refine your mesh to get accurate results. So as a result, it's gonna be expensive again because now you have to use finer mesh. The next one, which is very similar, is the second order of triangle or a triangle with 6 nodes. The nodes in the middle can capture curvature, so the shape function can reflect more flexibility. Therefore, it's not really bad, but it has the same problem. It's a triangle. It's not gonna capture the formation really good. It still has the problem with flexibility, but it's still cheap. The next one is a quad, which is a decent element. You can expect more flexibility, and it's really good for uh, the first iteration of your design when you want to see if there is anything wrong with the model or not. So you go with the quad 4 because it's not very time consuming. It's easy to use and easy to mesh. Not easier than Try because you can mesh almost any shape or really complicated shapes with triangles. Like if you have a circle, it's not gonna be really good with quad shapes, for example. Then you have quad 8, which is you can say the best one in 2D, but it is a bit expensive and time taking both to mesh and fix the problems on the corners and to solve the problem. There is another problem you need to know is that you better avoid using only one quad element uh, in a part. So if you want to model thickness of your part, you should avoid using only one element. Otherwise, you won't reflect, you won't get the accurate deformation. In 3D, we have the same similar shapes, but of course in 3D. We have TED 4, which has the same problem as Try 3. And then we have TED 10, even though we have better shape functions on the edges, but it has the same problem as other triangles. But it's really easy to use in the mesh. You can easily mesh any complicated shape without having any modeling error. But still, you shouldn't expect the best accuracy. The behavior of this kind is somehow better than uh, other types of or other we can say higher orders, but it takes too much time to solve comparing to other hex elements. The next one is hex 8. This is almost you can call it the generic type because you may always use this one. It's like quad 4 but in 3D, and this is very useful even as final element type when you want to start simulation. And of course, the perfect one in terms of accuracy is hex 20 with 20 nodes on a cubic shape. This is perfect, but really expensive. Here, the simulation starts to take really long to solve. But because of the shape function order, this is the most accurate one. So my recommendation is always avoid triangles and tetra shapes and always start with hex 8, and if there was problems then switch to hex 20. Now we can move on to mesh refinement by considering an example. As you may know, one method to find out the best mesh density is to gradually refine the mesh until you find out that the changes are not big anymore. So that's the best mesh probably. We're going to apply the same method. And a simple example, which I have the theoretical uh, answers here. We know the shear stress in this part is going to be half a megapascal. And of course, applied force is 500 Newton, and we expect a reaction force of 500. So I'm going to model this with different meshes in NX and see what's happening. Start by going to the modeling application. You have the size as 100 by 10 by 20 millimeters. Start sketching. Yes, and extruded by 20. Click OK. So we have the part ready. And now we can move on to the Prepost application. Here in the Prepost, we are going with the new FEM and simulation. We don't need idealized part. This is pretty idealized, and the rest are okay. And we want to do a structural. Click OK. Now the solver is okay. We want to do a linear static and click on create solution to create the first solution we want to have. And here we have our simulation. Then start by meshing. Since I want to do hex mesh, I will use swept option. I choose the source and this is my target. I want to use hex 8. If I go with automatic, it's going to be 4.5 and I click OK. So here we have the mesh. And if I go to physical properties, I have a solid here that I can edit. I want to have the same material in all simulations. I go with aluminum. I click OK. So we have aluminum applied to this. Then we going to switch to the simulation and start defining the force. Here I want to have the force on this edge of 500 Newton along this vector. Click OK. And then want to fix. And to fix this plate here. So as you can see now all the nodes are fixed. And the rest I think is okay, so we can move to solve and click OK. Here you can see the analysis is in progress. It's trying to open up. Yes, the solution monitor. And we don't have errors. We can close, and here we get result. The structural, here we have displacement. We can also see the stress. So let's go back. Here we know we should expect half a megapascal, but here on the maximum we have 16 megapascal of stress per element. We can also see nodal ones, which are higher. The element ones are distributed ones of the nodal ones. If we check, it's almost half because each element is sharing 2 points on the edge. So I will go back and change the mesh size and check result. Here we can also use different functions. For example, this is, if we go to absolute, we actually see the real deformation with 1-to-1 scale, but we can also scale it up like this. Also, we can go with the averaging between the elements, so you get a more smooth view of stress distribution. We can go to the identify results and see each element one by one, or select multiple elements to see the average at that point. Or we can go with mesh or different, we can, for example, go by number of maximum, like top 10 elements. So if I click this apply number, these are top 10 elements with average of 8. And if I go up like top 200 element, you see even the average is not reaching that half a megapascal. Even if I select all the elements, you still see we are not even close to half a megapascal. So let's write this down. 16, or we can say 17 megapascal, or let's actually pick one. Yes, 17 megapascal. We can save it here with the mesh size. So let's edit the data. Mesh size what was 4.72, I think, and we got 17 megapascal. Let's keep this here, so we're gonna change it later. Then go back, return, and I change the mesh. Here we need to activate meshing, and I want to change the mesh size. So I go back to the mesh parameters. This is around 4.5. 4.47. I now go with 3.5. You see now the mesh is changed, and I can just jump to activate simulation and solve it again. Simulation is done. I can move to the results and see the stresses. Now you see that now we have even more stress. If I go with picking elements, you see it's now 20.5. So I go back here, 3.47, 20.5. I go back and change the mesh again. I need to activate meshing first. Double click on 3D mesh and let's go to 2 millimeters, 2.5. Activate simulation and sorry, solve. Solution is completed. Result, structural, stress, elemental. Now we have 28, 2.47, 28. Should expand this maybe for 2 more solutions. I'm going to refine this twice. Activate meshing. 1 millimeter and solve. You see now it's taking a little bit more time. Going back to the result and stress. Now we have 48.2. And if I go to the applied force and you can see the applied force is like 500, the sum of it. And if I go to the reaction force and do the same thing, picking by maximum, let's say the 1,000 top elements, you see around 900, but this is the magnitude of the reaction force along X, Y, and Z. We are generating a little bit of moment around here, so we are pulling this place up as we push it along X-axis. We are also lifting it up. But if you look at the X reaction along X-axis and go with the top, let's say 2000 element, which should be all of the elements. You see the sum is sum of the reaction of all these nodes is 500, which we expected. Okay, now let's go back and do another one. Refinement, go activate mesh. And I go with 0.5 millimeter. This takes more time to mesh and of course more time to solve. Now this is really fine mesh. Let's see the difference in solution time. Even checking the model takes a lot of time. And we just have a simple cube. Checking is finished and trying to open Nastra to solve the problem. Okay, this took significantly more time, like half an hour to solve. Let's see the results. Here, go to structure, elemental stress. I can move it back to absolute, so we can. Here we have 148, or I can say 147, 148. Now, let me see if I can inverse. Yes. Okay, now let's see the results. Here, as you can see, I have the theoretical solution, half a megapascal, but here we are nowhere near that number. And the problem is when I find the mesh, the results are actually getting worse. So I'm trying to improve the mesh by making a finer mesh, but the maximum stress is going up a lot. And here we can check some other points, for example, the stresses, the average of the stress around different points, and still we don't have anything even remotely close to half a megapascal, even on average. So what is going on? This is called singularity in finite element method. The problem here is the point load and a sharp corner. These two do not exist in reality. In reality, you don't have a sharp corner. I mean, even the tip of a needle has a radius. It's not just one point. So everything has a radius, even a small. There is no real sharp corner in reality. And same with the point load. It's not possible to apply a load on a fixed point. There is always a radius that is point being the load is being applied. Now here is what is happening. I started with a quartz mesh here, you can see, and the stress by the definition, the shear stress or tension or compression stress is force divided by the area. So it's going for this red element, it's going to be the force 500 divided by area of this element. When I find the mesh down here, you see the area is getting smaller, and the finer mesh, the area is smaller. And you can see here that the area is going to zero. As a result, the stress is going up to infinity because now the area of this element is really small. Now, how we can deal with singularity? There are generally four solutions that we are going to look at it, but The main solution you will usually use is to ignore the hotspot. So that's why it is really important to actually uh, detect the hotspot and ignore the hotspots or where singularities are happening and check other places for the stress. The other solutions are consisting using mesh bonding, uh, connecting the mesh, two meshes with different methods than connecting the geometry, which I will show, or using chamfer or using a fillet, as these are solutions that will make the geometry more real. So you are trying to make your model more real, which of course takes more time to model. Now in our next lecture, I'm going to do an example with each one of them and compare the result to see which solution is better.